In this video, we are going to look at the stoichiometry of gaseous substances, mixtures, and reactions. By the end of this video, you should be able to use the ideal gas law to compute gas densities and molar masses, perform stoichiometric calculations involving gaseous substances, and state Dalton's law of partial pressures and use it in calculations involving gaseous mixtures. If we're going to calculate density, we can start with the ideal gas law, PV equals nRT. Now, density is mass divided by volume. We do have volume here, but we don't have the mass. So if we rearrange this, we get N divided by V equals P divided by RT. So this gives us volume in the denominator over here, but number of moles, not the mass, on the top. However, the molar mass is equal to the mass of a substance divided by the number of moles present. So if we take this and multiply both sides by the molar mass, our units of, or our moles themselves will cancel out. And we have mass divided by volume left, and pressure times the molar mass divided by RT on the other side. So we can get the density, M over V, of the gas by plugging into P times molar mass divided by RT. If we wanted to find the molar mass, we would start with the ideal gas law. N equals PV over RT. So I have this solved for the number of moles. But what I really want is the molar mass, mass divided by number of moles. So if I invert both sides, I get 1 over N equals RT over PV. And then I can simply multiply both sides by M to get M over N, the molar mass, equals MRT over PV. When I have mixtures of gases, each gas contributes to the overall pressure of my sample. And the total pressure is equal to the sum of all of the partial pressures. So if I had 3 tanks, one with 300 kilopascals, one with 600 kilopascals, and one with 450 kilopascals, if I combined all 3 tanks, all of the gases in them, into one tank of the same size, I would simply add up all of the pressures of those individual gases to get the total pressure of the entire gas together. However, if I have a mixture of gases, often I want to know what portion of the pressure is being created by one specific gas. In order to do that, I need to know what's called the mole fraction that gas makes up. So the mole fraction is represented by a capital letter X, and it's equal to Na, the number of moles of substance A, divided by the total number of moles of gas particles altogether. So if I take that mole fraction and multiply it by the total pressure, I get the partial pressure that's being exerted by gas A. This is especially important when we're collecting gases over water. So sometimes when we're trying to collect a gas that's being produced by a reaction, we'll attach a tube to it and have a flask filled with water and the tube going in there, and then as the gas is produced, it starts filling up the flask, and I end up pushing the water out and getting the gas collected in the top of that flask. Now, when you're trying to find out how much gas you actually collected, it is important that you end up moving that flask up and down so that the water layer inside is equal to the water layer outside of the flask, so that we know the atmospheric pressure is equal to the pressure in the flask. So if I have the pressure inside and outside the flask the same, then I can very easily measure that volume of the gas. However, one thing to keep in mind is it's not just the gas that I was trying to collect in that flask. there's also going to be some water vapor in there. So we can find the vapor pressure of water at a given temperature and then subtract that vapor pressure out, and we have the pressure of just that gas that I'm looking for. The last thing that we're going to look at is stoichiometry with gases. And when we've done stoichiometry problems with gases before, we've said, all right, let's say I have 5 liters of nitrogen gas that's reacting, and I want to know how many liters of ammonia gas I'm going to end up with. We've converted from the volume of the gas to moles, and then used our mole ratio to get to moles of ammonia, and then converted back to liters of NH3. And we've used this 1 mole is equal to 22.4 liters of any gas. But we need to remember that that's only at standard temperature and pressure. So when we look at the units canceling on this, we have liters of N2 canceling, then moles of N2 canceling, moles of NH3 canceling, and I have the liters of NH3. However, if you notice, we have this 22.4 liters on the bottom and the 22.4 liters on the top. So because the numbers are the same, because if I have the same conditions, an equal number of particles will occupy the same volume, I can actually skip that step and just have 5 liters of N2 and use that mole ratio. The same ratio is going to occur for volumes as does for moles if I'm talking about a gas, assuming that all conditions of temperature and pressure remain constant throughout the experiment. So I could also say 5 liters of N2 and then 1 liter of N2 produces 2 liters of NH3, and that will also give me a correct answer. And that's without having to assume that I'm under standard conditions either. If I'm not under standard conditions and I want to know what volume I'm using or producing of something, I can do this regular stoichiometry, calculate how many moles of the substance I either need or will be producing, and then use the ideal gas law to calculate the volume from that.